Good morning, everyone. I'm Sriram and I'll be talking about our paper, Gestop, Customizable Gesture Control of Computer Systems. What is Gestop? Gestop is a framework for interacting with computer systems using hand gestures. It presents a simple way to execute arbitrary computer actions using arbitrary hand gestures. It is customizable and extensible, which means that it allows end users to add new gestures to be detected and map them to custom actions. Some sample use cases that we've thought of are using it as a mouse replacement, using your hand gestures to replace the touchpad or the mouse, and utility scripts, which can use to set up your working environment or any other thing that any action you perform commonly, and possibly a better way of making presentations. Instead of fiddling around with clickers, you could use your hand to control when to move to the next slide and so on. What is our motivation? The traditional way of interacting with computers is through keyboard, mouse, or similar hardware devices. These devices are not as intuitive or as universal as hand gestures, which can provide a touchless way of interacting with these devices. The main barrier to widespread adoption has been the technical hurdles. There is the problem of self-occlusion, which means that the hand contorts on itself, making it hard to recognize that it's an actual hand. And there's, of course, the problem of multiple hands in the single image, which could confuse any recognition device. There are existing repositories which deal with this problem of gesture recognition, but they either tend to focus on key point detection, which is just the first aspect of gesture recognition, or they provide limited gesture recognition, which means they only detect a few gestures. MediaPipe is one such library which provides key point detection, but not an end-to-end use case, as we are proposing here. We present a first such end-to-end architecture and tool for gesture recognition by building on MediaPipe. What are hand gestures? Hand gestures are simply a non-verbal form of communication using bodily actions. We have two types of hand gestures. The first is called static gesture, which means that its meaning can be inferred from a single image. And the second is called dynamic gestures, which means that you require a series of images or a video to infer its meaning. An example of a static gesture is given on the bottom right. The gesture name is Spider-Man. So this is the architecture of our system, Gestop. In the upcoming slides, I'll be going through each component in detail, and we'll come back to this image later as well. So the first component is the MediaPipe component, which is an open source library by Google, which provides cross-platform machine learning solutions. Once the solution is called MediaPipe Hands, it provides high performance and high fidelity key points from each image. As you can see on the GIF, right, you have 21 key points being constructed from a single image. These 21 key points are basically 4 for each finger and 1 at the base of the palm. That gives us 21 of X, Y, Z coordinates. And the output is a 21 into 3, 63-dimensional vector. So that was the first component of Gestop, which is MediaPipe. It generates the key points, and then these key points are transmitted to the gesture receiver. Okay, now we've reached the gesture receiver, which is the heart of the application, which acts as a control tower for the other components of Gestop. It transforms the key points into the format expected by the next component. The problem here is that MediaPipe provides absolute coordinates, which means that the same gesture performed in different parts of the screen will have different coordinates, which is a behavior we don't want. Our solution is to use relative hand coordinates. This means that instead of passing the key point value directly, we subtract it with the value of the key point next to it, providing the relative distance between these two key points. And this is space invariant and independent of the position the hand is on the screen. Okay, so the gesture receiver transforms the key points and then sends it to the gesture recognizer. Before we get to the gesture recognizer, let's talk data sets. So for static gestures, the data is collected manually. The gesture is performed and held in front of the camera, and the data is written to disk, giving us a simple data set. For dynamic gestures, we make use of a data set known as Shrek. It provides data for many common dynamic gestures, such as swipe up, pinch, rotate clockwise. Two GIFs here demonstrating two gestures that are in Shrek. Okay, now we're at the gesture recognizer. These transformed key points are fed into the neural networks, which then detects the most probable gesture that has been performed. For static gestures, we have a simple two-layer feed-forward network with linear layers. The features are the relative hand vectors, which I discussed in the previous component. One problem we face here is filtering invalid gestures. The network detects gestures at every single moment in time, which obviously we're not performing a gesture at every single moment in time. And we need a way to filter out these invalid gestures. We do this by making use of a dummy gesture we call the bad gesture. And the network is artificially biased to choose this gesture. So this makes sure that unless the network is very confident that a gesture has been performed, the dummy gesture is selected. For dynamic gestures, we use a recurrent neural network. The features, along with the relative hand vectors, which I've already discussed, there are two other augmentations. The first is called the time diff coordinate, which means the value of the key point in the previous time frame is then appended to this. This gives the neural network a sense of where the hand was in the previous frame and how it is moving. And we have the absolute coordinates as well, which are just the normal pixel values, normal coordinate values, which again tell the neural network where the hand is, because unlike static gestures, dynamic gestures are not space invariant and require information of where the hand is to recognize. One other problem we faced was detecting the start and end of a dynamic gesture, which is a hard problem. There is no way to reliably detect when a gesture starts and ends. We work around this by utilizing a signal key. When a signal key is pressed down, then the neural network starts grabbing frames. And when this key is released, this entire sequence of frames is fed into the neural network, the current neural network, to detect a dynamic gesture. And finally, the Shrek data is recorded using a 3D depth sensor camera, whereas during inference time, we are using a MediaPipe with a normal RGB camera. There is a domain mismatch between these two cameras, which leads to some loss in accuracy. Okay, so that was the gesture receiver, a gesture recognizer. The gesture recognizer detects and classifies the gesture and returns the gesture name to the receiver, which then passes this name to the gesture executor, which is the last module. The gesture executor is the last module. The job of the gesture executor is to execute the action corresponding to the detected gesture. These actions can be either Python functions or shell scripts. You can use Python functions to interact with the computer through a mouse or keyboard, or you can even use shell scripts for more complicated operations, such as setting up your working environment, or as a hotkey to open commonly used applications. On the right, you can see a GIF of me performing the 7 gesture, which is mapped to the left mouse down action, which allows me to drag a window by performing the gesture and then moving my hand. As I mentioned before, Gestop is customizable, and the first way in which it is customizable is through custom actions. Gesture and action mappings are stored in a config file in the following format of gesture name, type, and function name, where type would be either Python or shell script, and function name would be the name of the function to be executed. Consider a function take screenshot, which, as the name suggests, takes a screenshot. When this function is called, the print screen key is pressed and then released, taking a screenshot. To execute this function, when the pinch gesture is detected, you would add this mapping into the config file of pinch, py for Python function, and take screenshot for the function name. The second way in which Gestop is customizable is through new gestures. You can collect data for new gestures using the included scripts. You retrain the neural networks and then add the new mapping in the configuration file. And that's it. Your new gesture is ready to be deployed as part of Gestop. I will now play a demo video and walk through what is happening in the video while it is playing. So first, I perform the 7 gesture, which is mapped to the left mouse down action, and I drag a window. And left mouse down again for the click. 4 for the right mouse down action, and 7 again to open it in a new tab. The Spider-Man gesture is mapped to the scroll function, and as I move my hand, you can see that the window is scrolling. Now I'm performing some dynamic gestures. I perform the swipe up gesture, which increases the brightness. Swipe down to decrease the brightness again. Here I'm performing the rotation clockwise gesture, which increases the system volume and to decrease the volume. I perform the swipe right gesture, which then move my workspace to the right. If you can see on the top left, you can see the workspaces, which then move when I perform the swipe gesture. And yeah, I performed a grab, which took a screenshot. And finally, swipe left to move to the next workspace. So that was a demo of Gestop in action. For future work, we aim to enhance the accuracy of the dynamic gestures detection. As mentioned before, there is a domain mismatch between Shrek and MediaPipe. Then efficient incremental training of new gestures. As of now, the whole network has to be retrained whenever new gesture is added. We aim to rectify that with efficient incremental training. And finally, to deploy it as a PyPy package for ease of deployment, such as say pip install Gestop and be good to go. These are some of our references which we've used in building Gestop. And yeah, that's it. That's all from my side. I'll be taking any questions. Thank you.